Welcome back. Till now, we were practically implementing different components of verification and taking our first steps with verification. In order to make progress with our verification effort, we need to know some basics of verification theory. So we'll take a short break and try to cover the minimum amount of theory that is required for us to make progress and then get back to our implementation phase. Our verification effort till now was to cover each and every row of a truth table. So we had a DUT which had two inputs A and B and one output Y. And what we did is we constructed a truth table saying A, B, Y and covered 0, 0, 0, 1, 1, 0 and 1, 1. And then we wrote a test bench and test case where we applied each row to our DUT and checked whether the output of the DUT matched the expected output that we had predicted. If we adopt this method for verifying any kind of non-trivial design or even a simple design, say a 32-bit adder. So in case of a 32-bit adder, what we have on our DUT is input A and input V, where each input is 32-bit wide and an output Y. So now our input total A and B, they are 64 bits of input. So to iterate over all the possible values of A and B, we would require 2 to the power 64 rows in our truth table. And 2 to the power 64 translates to a very large number. This is equal to somewhere around 1800,000 trillion operations or 1800,000 trillion rows. And if we take any of our commercial CPUs, either from AMD or Intel, a single core in that CPU will require more than 100 years for verifying such a design. So the approach that is normally taken during verification is a twofold approach. One is with directed test cases and the second is with random tests. So with directed test cases, what we do is that we intelligently select a subset of our 2 to the power 64 vectors in this case and try to determine what are the combinations that are most likely to catch bugs. For example, if what we are verifying is an adder operation, then we have a case where we say 0 plus 0 gives us a 0, 0 plus 1 or 1 plus 0 gives us a 1, and a 1 plus 1 gives us a 0 with a carry, and similarly a 1 plus 1 with a previous carry will give us a 1 with a carry of its own. So given that these are our combinations, we can say that I'm adding my A input is 0, my B input is 0, and we can see whether the output of this adder is 0. Similarly, I can say that my A input is a hex value of all A's and my B input is a hex value of all 5's. That will translate to this combination, and similarly if I swap A and B, it will translate to this combination. And then finally I can do something like my input is all F's and maybe just add 1 to it, or I can add a value of all F's to this, and that will basically translate to this. So once I have selected this set of vectors, which are most likely to cover different scenarios and trigger different errors, I will have this reduced truth table with which I will write out my test cases and I will verify this adder. So typically for directed test cases, if we don't have much knowledge about what kind of operation is happening, or if the operation is too complex for us to comprehend, then what we do is we do a min max. So in this case, a min will be 0, a max is all f's, and we do all combinations of this. So min with min, min with max, max with min, and max with max. So we do all combinations of this. Then we do a walking one. What this basically means is that we have all zeros, then one at the LSP space and everything else is still 0. Then one at bit location 1, all the other bits are 0. Then one at bit location 2 and all the other inputs are 0. So that would be a walking 1. And similarly, a walking 0 would be all 1 with 0 at LSP, then 0 at LSP plus 1, and so on and so forth. Alternate ones and the zeros are basically patterns of AA and 5, 5. So with this set of tests, we will have some directed test cases. Now, given that this was our space of all 2 to the power 64 vectors, with directed test cases, we managed to hit only a small set of all possible tests possible. There might be some error over here, which we have not targeted with this test. Or maybe there is an error in this region, which we have again not targeted with this test. So the next thing what we do is that we randomly select test vectors. And we hope that one of this test vector end up in a region which triggers the error. So a test vector might end up over here or it might not end up over here. In case it ends up over here, it will trigger a error. And while debugging the error, we will fix this class of error. Similarly, if it triggers something due to this, then we will end up fixing this class of errors. So that's what happens with random testing. And normally in our verification flow, we don't just select one. We don't say that we'll only do direct test, or we don't say that we'll only do random. We do a mix of both. That is, we do directed for patterns that we feel are more likely to hit error cases, or more likely to unveil different classes of error. And then we do random test after exhausting all our directed test cases, in the hope that we end up hitting something which was not hit by our directed test. And in terms of verification effort, with directed test, our effort in creation of the test environment is very less, because all that we are doing is we are writing out our truth table. In case of random test, writing out the truth table won't help, because we are randomly generating the value of A and value of B. So whatever logic is being implemented in our duty, we will have to implement the exact same logic in our test bench, so that we can provide A and B to this and get the output Y. So this logic which is used for verification is called as a reference model, or it is also called as golden model. So the effort for creating the test environment with random tests is more. The effort for writing test cases with random test is relatively less, because once we have defined the environment and once we have defined our random number generators, then we just need to provide our list of constraints and the generator will generate all the vectors for us. Whereas in case of directed, we have to manually write out each line of our test vector and then apply it. So on the test case for directed test, the effort is more. In terms of simulation time, for directed tests, the effort will be relatively less. One, because our test case and test environment is simple. And second, we are just testing the cases that we are interested in. So for example, if this was a 2 input gate, then I know that there are only 4 possible values. So with directed, I will just test for 4. But if I was randomizing the input A and B, then if I just try to hit it with four values, for example, if I'm randomizing A and randomizing B, I might get something like A0, 0, 0, 1, and B I might get 1, 0, 0, 1. And this is not covering all the cases. I might have to generate vectors for more than four cases in this case. So let us say I generate for 15 or 20, and with that I will get a sufficient coverage over this. And if I want to get coverage over a sufficiently large space of this 2 to the power 64, then the number of vectors which I will have to generate will also have to be sufficiently large. So since there are a large number of vectors with random tests, the simulation time is going to be more. And also the case generation or the vector generation and the model will be much more complicated. That will lead to increase in simulation time. Then hitting known corner cases, for example, if it is an adder, I know that my corner cases are 0, 1, 1, 0, 1, 1, 0, 0, and then 1, 1 with a carry, 1, 0 with a carry, and 0, 0 with a carry. If these are my known corner cases, then the chance that I will hit all the known corner cases with directed test case is very high. With random test, I might not hit each and every one of these cases. And with directed test, if this is my directed test set, I am not going to hit any corner case over here or here. Whereas with the random test, I have a probability of hitting this corner cases as well. So the approach that is normally used is we use directed test initially for doing basic flow flush of our DUT. And then we move on and write directed test cases for all the cases that we have identified. After this, we switch to randomization. For example, let us say that there are 20 vectors in for my directed test case. I will then randomize my inputs, say my input A and B. I will start randomizing them. And I might run this for, say, 20,000 vectors. And I might run the same test with multiple different seeds so that it hits different locations in my search space. So for regression testing, we depend more on randomization to catch our bugs. And once we have done this, there are two things that we use for sign off. One is code coverage and second is function coverage. So code coverage is basically telling us that whether we have tested each and every line of code that was written. And functional coverage is more from the specification side. So functional coverage tells us that whether whatever was specified, whether we have test cases which cover that. And code coverage is reported by your simulator. So Icarus Verilog does not natively support dumping of code coverage. There is a separate plugin called Covered which helps us figure out code coverage for Icarus Verilog. Most of the other simulators, they natively dump out the code coverage reports. So when we are speaking of code coverage, there are a few parts over here. For example, if we have some code, let us say if A or B, and then a few lines of code, else a few lines of code. So if I look at it as just statements, then I need to ensure that during my verification, each and every one of this line of code has executed at least once. So ensuring that each and every line of code has executed is called as code coverage. Now, in this particular section of code, there are two separate branches. One branch for true and one branch for false. So ensuring that we cover both the true and false case in our branch is called as branch coverage. Now, transition from true to false or false to true happens on the value of A and B. So my A and B again will have four different values in this case. So 0, 0, 0, 1, 1, 0, and 1, 1. So ensuring that transition happens from false to true So this was our false case to true because A changed, or because B changed, or because both A and B changed. Okay. Similarly, a transition from true to false because A changed, B changed, or both A and B changed. So this set of transitions, if we cover, then this is called as toggle coverage. And once we have this set of coverage values, that is code, branch, and toggle, then we are more or less assured that we have covered our code. That is, we have verified whatever was written. On top of this, we might want to cover FSM coverage, where we are not just seeing whether a transition happened from one branch to another, but we are trying to extract the state information, and we are trying to see whether we have covered all possible state transition which are allowed in our circuit. So this set of coverages are covered under code coverage. Functional coverage is something which the verification engineer needs to write. So with functional coverage, what we basically do is we go through the specification. So this might be my architecture document, or it might be my design document, or it might be my protocol specification. So we go through each one of this. We go through it line by line. And wherever we see a particular statement saying that this is the way the design is supposed to behave in this condition, we make a note of it. And for each such condition, we either write an assertion or we put a coverage bin. So when we speak of assertion, this is basically saying that if X happens, then Y will happen. Or if X happens, then Y will not happen. Or some other conditions like this, that if X happens, then X will keep happening for at least 5 cycles. So all this behavior, if we find it specified in any of our design document, then we write corresponding assertions for them. So typical case would be when we speak of a ready enable protocol. We are saying that if ready goes high, then at some point enable will go high. We are saying that if ready goes high, it will not go low until and unless there is a transaction, that is until unless there is an enable. When we are saying that a case that enable going high while ready is low cannot occur. So once we start seeing this kind of specification in our document, we can write assertion for each one of this case. Whenever we find such specification, we try to see if it can be covered, if it can be converted into a bin. So an example of bin would be, again going back to our XOR gate or OR gate, where we had A, B, and Y. So here we specify that A can take a value of 0 and 1. B can take a value of 0 and 1. And Y can take a value of 0 and 1. And then we say that we want to test out for all combinations of A and B. So this is called as cross coverage. Once we have documented this set of pins, we can write specific code in our Cocotb test environment to ensure that whatever input is given to the DUT pins A and B, we record those inputs and we try to match it against this table. So whenever we see an input to A, we see whether it is 0 or 1. Similarly, B, we see whether it was 0 or 1. Y, we see whether it was 0 or 1. And then at the end of the test, we say which of these parameters were met and which of them were not met. And that tells us that how much of our functionality we have covered. So on the functional side, what we are basically trying to measure is that whether we have hit all the bins, whether we have hit all the crosses, then whether any of our while assertion which we had declared, it can either be a positive assertions, which means that we are saying that if X has occurred, Y should occur, or a negative assertion, that is, we are saying if X has occurred, Y should not occur. So we will see whether any of this assertion has either occurred or has not occurred. That is, whether the trigger for each of this assertion, whether it has taken place. If all the assertions were triggered and the assertions did not fail, then we would say that we have also met our functional coverage goal. So these are the metrics. Code coverage is something that is measured by simulator, and functional coverage is something that we are going to code. That's all for this discussion on the theory.